So when you ride a bike over a bump or drive a car over a pothole, what you feel are damped oscillations. We can model these oscillations with a mass spring damper system. Let's use MathCAD to create that model. We start off with a blank worksheet. I can change things like the grid resolution. I can go ahead and make the margins narrow so I have more room to work with. And I can also change the orientation so it's landscape. Let's go ahead and give this worksheet a title. I'll keep it simple, just call it Mass Spring Damper. I will also pick an image to insert into this document so you have an idea of what I'm trying to model. Next, I define the equation for the force provided by the spring, which is just negative k times x. Notice that x is dependent on t, which makes the force dependent on t. I can do the same thing for the force provided by the damper. In this case, that's going to be proportional to the velocity, which is dx dt. To get the dx dt symbol, I go over to the Math tab and use the calculus operator. I can now take the derivative of x. And then finally, for the sum of forces, which is just equal to F equals ma, I need to take the second derivative of x. So those are my equations. Now that I have those equations, I want to go ahead and actually have MathCAD solve this ODE, ordinary differential equation. So let's go ahead and apply some values to my mass damper and also spring. I will give it a mass of 2, a damper of 1, and a spring constant of 3. Next, what I'm going to do is use a solve block. So I'm going to write the same ODE equation, but this time I'm going to use the prime notation. So I get m times x double prime plus b times x prime plus kx. And that's going to be equal to 0. And then I'm going to offset it with an initial value of 1. So I'm going to hold x initially at a position of 1 and then let it go and then see how it oscillates. And so to see how it oscillates, I need to use the ODE solve function. To find that, I can go over to the functions search bar and just search for ODE. That will populate the solve block with ODE solve. And I can just go ahead and put in that I want to solve for x. And I can also say I want you to solve for x all the way up to t equals 20. I'm just going to move some things around so it looks a little bit prettier. And now that I have a function that's been solved by the ODE solve function, I can go ahead and plot it. So when I go ahead and add the plot, I just need to specify that I'm plotting x, which has been solved by the solver, and then I want to plot that versus t. So if you take a look at this, and I'm also going to adjust the limits so that I'm going to start from time 0 and just look at it until t equals 10. So let me move this plot to a new page so you can take a look at it a little bit closer. And there it is. There's my damped oscillations. Now what I want to do is approach this a little bit differently by using the Symbolic Engine built into MathCAD. So I'm going to open up a new worksheet and I'm going to set up the same layout as before. And I'm going to copy and paste the picture in the title from the previous worksheet so I can just use it here again. Now because this is an ODE, I know that I can go ahead and express the solution, or x, in terms of an exponential. So it's going to be a times e to the rt, where r stands for the root. And I can go ahead and take the derivative of this, the derivative, as you remember, just using the derivative operator. And I can actually have MathCAD evaluate this symbolically. That's what the arrow means. Notice how the derivative is now expressed in terms of symbols or variables. I can do the same thing for the second derivative. And now I can apply the whole equation. So m times second derivative of x plus b times the first derivative of x plus kx. And I can have MathCAD basically evaluate that for me. I can even clean it up by using the factor modifier, and that will actually collect the like terms. Next, I'm going to copy and paste that equation, but this time I'm going to set it equal to 0 and then have MathCAD solve for what the roots are. Now, this is a second order ODE, so I would expect 2 roots. I can go ahead and save this off as the variable r, and as you can see, r now has 2 different values. I can substitute in the values in for m, k, and b, and then in this case, if I use 1, 5, and 6, MathCAD will plug it into the equation for me and give me the roots of -3 and -2. Because I have 2 roots, I need to actually modify my solution for x. So I'm going to have an a0 for the amplitude of the first root, and then an a1 for the amplitude of the second root. And just like before, MathCAD will evaluate those symbolically. As before, I need to define two initial conditions. So I can define a x0 or x at time 0, and that's going to be equal to a0 plus a1. My velocity at time 0 is going to be obviously the derivative of x evaluated at time at t equals 0. So I use the symbolic evaluation and then use the modifier assume t is equal to 0. Now what I can do is set the x0 and the v0, the initial position and velocity, to some arbitrary values. So let's say I want to set, just like before, I want to set the initial position to a and set the initial velocity to 0. And now what I can do is, given these conditions, solve for what a0 and a1 are. Once I have a0 and a1, I can plug this back into the original equation. So I can redefine what x is fully and symbolically. So this equation is going to look quite messy. In fact, it won't fit all the way on the screen. So maybe what I really care about is just a specific value, right? So what I can do is just what I showed you earlier is to substitute in some values for the mass, spring, and damper, and then I can also specify the initial position. So have that equal to 1. So I'm going to use the same values as before in my previous ODE solve example, right? So plug in the same values, and just like before, I'm going to go ahead and put in a plot, and I'm going to plot x of t versus time. Right? So now if I compare this plot to the original plot, you should notice that they look exactly the same, except this is now all done symbolically.